Most physical quantities that we observe are analog. The simplest ones, such as weight or temperature, are measured with a scalar, which is a number with units, so you could have newtons for weight or degrees Celsius for temperature. And the reason it's analog, you can take any value here. It can be 20.1 degrees, 20.15 degrees, etc. You're not limited to zeros and ones there. When we want to measure any physical quantity in digital form, unlike the spring scale and the thermometer we showed on the previous slide, an analog device sensor converts the quantity into a voltage. For temperature, the device is called a thermistor. For forces and weight, the device is a force sensor or strain gauge. The voltage is then converted, so we have another conversion going on here, from its natural analog value to a digital value. And we use an analog to digital converter, or ADC. The ADC will convert the voltage to electrical pulses, on and off. On represents ones and off represents zeros that are calibrated to the quantity being measured, whether it's voltage, temperature, weight. It is translated into decimal form, which is what we normally read, right? Numbers like 1, 2, 5, and then displayed. Converting sound into digital form is a little more complicated than converting a weight or temperature, but it's based on the same idea. The first thing is we have to use a sensor to convert the sound to voltage. So here, this is representing the molecules closely packed to each other when this guy's blowing a horn, and here they're a little farther apart when he sucks in on it. Can you guess what kind of sensor we'd use here for converting sound, for starting the process? We use a microphone. All right, we've got the sound waves coming in here. The microphone converts that sound to an electrical signal, which will be a voltage that will vary with time. And that's varying according to how loud or what frequency the sound is. We now have to convert this analog signal, which is the red line, into a digital signal. So the way we do that, we pick off points on it. And we take these blue dots. Here we're sampling every this amount of time. So time is on the x-axis here. So every bit of time there, we say, where is that curve? Well, it's there, it's there, it's there, and we're going to record those numbers. What if we just sampled at that point? What would the curve look like? Well, it would be like straight lines, and it wouldn't really represent what the curve is doing very well, would it? How would we get this more accurate so we could represent the curve with a number of blue dots? Just increase the frequency of taking the blue dots, right? So if I took a blue dot in shorter periods of time, it would more closely resemble the curve, okay? I mean, let's be extreme here. Let me just erase all that, because this is a key point. Remember, the red is the actual sound, and we want to convert that into digital. What if I only sampled twice in this entire interval? I would sample right here, and I would sample here. Well, let's make it 3 times. I'd sample here. What kind of graph would I connect with those points? I would have like that. Does that look anything like this? No. So what I have to do is sample more frequently. And that's what we're calling this. Sampled is another word for measuring at regular intervals. If I wanted to record a CD and transmit that to digital, those intervals would occur at a frequency of 44 kilohertz. 44,000 times per second you would do the sampling. That would give a representation of this curve pretty close to what it really is. Once we get all these points, the voltages at each one of these points, we would convert the measured voltages, the blue dots, into 2 byte, which is 16-bit data packets that are then ready for transmission or storage. Now, this sound wave, if we just sampled at the blue dots where we've shown there, which won't give a really great representation, but it does show the curve going up, coming down, going up, and you just don't know what's happening in between the points, so it would just connect them. Not exactly precise. But when we convert each of the voltages, like that's 4 volts, this is 6 volts, and we convert it to binary, this signal here that will be transmitted has replaced that wave, that sound wave. What if we have a photo we want to convert and send somewhere? Well, converting an image into digital form uses the same principles as a digital measurement of temperature or sound. Temperature, one measurement is made, right? It's 42.3 degrees. For sound, one measurement of amplitude is made 44,000 times per second. Now for an image, many measurements are made at once. Why? What's different about images? Well, we're going to cover that in the next few slides. We'll start with black and white. And don't worry, we'll move on to color. We have a black and white image of a sailboat. The camera sensor divides the image into small squares called pixels. I think you've heard of pixels. Well, if you haven't, here's pixels. And that comes from the phrase picture elements. See, P-I-E-L, and they put an X in there because it sounds cool. A 2MP HD camera has 1920 by 1080 pixels. What does that mean? It means it would have 1920 of these boxes here, because each box is a pixel, and then you'd have 1080 across. And actually, I'm not sure which one's across or up and down, but it's the same concept. You multiply those together, you have 2,073,600 pixels. These little guys here. Here we clearly don't have anything like that. We have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 10. We have 100 pixels here. Now here we only have two colors, black and white. So our camera sensor pixel will read C black if more than half the square is black, or white if more than half the square is white. So this is viewed as white. This is black, and let's see. This one here would be white, more than half the square is white. Here, more than half the square is black. Okay, so it goes through and does that. And here are the pixels that are colored black because more than half the square is black, and then the others are white. So what we have here are the squares that white was submitted. Okay, they had more than half of it was white. They still had some black there, but more than half was white. These squares have no code because nothing was going on there, right? You didn't have a square with any black. Next step, replace every white square with a 0 and every black square with a 1. So the top one's easy. That's a bunch of zeros. There we go. The next one, same thing, zeros. The next line, let's see, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. 2 ones, 2 ones, and 3 zeros. And you go down the line. We really didn't have enough pixels to make this right here look like a sailboat. That could be almost anything. How can we make it look more like a sailboat? More pixels. Okay, so that's what we would do there. We would overlay a different screen of pixels to get a little better detail to make that look more like a sailboat. Okay, that was black and white, but most of the time we're interested in color pictures. So how do we do that? How do we do colored digital photos? Think about it for a sec and go on to the next slide. This time we have 3 sensors for each pixel. 1 red, 1 green, and 1 blue. Mixing red, green, and blue creates all the colors. The intensity of the red, green, and blue components of the light on each pixel is converted to a voltage by the sensor, which is then converted to a binary number. So for black and white, we had 1 light sensor per each pixel, it was either light or not. In color, we have 3. And when you mix them all together, you get the real color of the object. Now, how do we code the red, green, and blue components? Well, the more bits we use, the greater the color depth or number of digital colors. If we only use 8 bits, the colors are broken down like this. There's not that many colors to describe all the different types of red you have. If you have 24 bits, see how it kind of blends a lot better? You have a lot more ways to describe what color you have. Next step would be videos, digital videos. Any movie or video is just a string of images made by taking many photos spaced out evenly in time. Digital videos made on a mobile phone or camera consist of 24 digital images taken per second. That would be normal speed, or 240 images taken per second. That would be for slow motion. Digital displays, which are used in HD TVs, smartphones, and computers, the way they display a picture is very similar to the way a digital camera takes a photo. The displays are composed of a regular array of pixels, each containing 3 color elements, red, green, and blue. The digital representation of a picture, it's a string of binary numbers, It specifies the intensity of each color element in each pixel. The HDTV, smartphone, or computer uses that information to set the voltages for the light intensities for each color element in each pixel. That's a lot of words there. So if you'd like, please pause and just read them again. It's pretty cool stuff. Now, whether with sound or images, the more measurements you take or the more samples, the greater the number of bits used to represent the measurement, right? So there's two things here. More measurements, that's one thing, and the greater number of bits used to represent the measurement, the better the reproduction. So if you increase your sampling frequency going from bottom to top there, and also you increase the bits, okay? You start with 8-bit digital. Probably should have started at the top here. Here's my analog wave. This is exactly what's happening. This is my sound wave. If we represented with 8-bit digital, that doesn't look much like it, does it? Now, I increase it to 16 bits, and I increase the sampling frequency. A lot better, but still not really smooth. And then finally, 24-bit digital, looking pretty good. Once again, not quite the analog signal. Many audiophiles, and that's people who really like high-quality sound reproduction for mostly music, I would imagine, they say they can tell the difference between an analog reproduction of music and the best digital reproduction. So what they're saying is they can tell the difference with their ears between that and this. Which is one of the reasons that vinyl records are back in style. Those are analog. There's no digital going on there. I myself can't hear the difference, but I'm sure some people can. And again, let's go over to images. The more measurements, that's one factor, the more measurements or samples you take, combined with the greater number of bits used to represent the measurement, the better the reproduction. So here is a 480p TV resolution with 640 by 480 pixels. And on the right, you have a UHD TV resolution. Look at how many more pixels you have here, right? And you got to multiply them together to see the total amount of pixels. So clearly, this has a lot more pixels. And it looks a lot better. It represents more of what reality looks like.